Hello, everybody. We'll now be introducing the very famous problem which has come up in the recent SSC examination. We have seen it in selection phase 13 examination. Selection phase 13 examination. This is basically called the Monty Hall problem. This is the Monty Hall problem, and it has been taught by a lot of teachers, and we are definitely and continuously looking at it, how things are going. So, first of all, I will take you to the theory of the problem, which is very important for you to understand. Okay, everybody tells you, you must have heard almost everywhere that there are three choices that are given. You have selected the A choice, and the host tells you that B choice or C choice has a goat. Then would you be switching to option B or would you be staying with option A? So this has been the problem, and most of you understand it, but there is a very slight touch or there is a slight tinge of probability which is involved in this question, which is what makes it just a very tad bit difficult in the examination. But I would give you a preliminary problem first to solve. Once you solve that problem, then you will be able to analyze and understand that the entire Monty Hall problem is just a two-step problem. It is nothing more than that. All right. It's just a two-step problem and it is nothing more than that. So the host tells you that switching leads to a more probable outcome. It means your chances of winning become higher when you switch. Okay. I'll tell you how this basically works. This is the most important slide of the entire presentation, that you have to understand and read this entire thing. If you understand this very well, you will be able to get it and you will be able to crack the problem very easily. What do we say? That there are three doors, and in the Monty Hall problem, this is a classic case of Monty Hall problem. Okay, this is a classic case of Monty Hall problem. That is why there are only three doors. Behind one door is a car, and behind the other two are goats. You pick one door, let's say door one. There are three doors, one door, two door, and three doors. You choose door one. At this point, your chance of picking the car or your chance of getting the car is 1 by 3. Why is it 1 by 3? Because there are a total of three choices and you have chosen the first one, or let's say the second one or the third one. Then one out of three definitely have a car. So your chances of winning a car are 1 by 3 in your door number one choice. Okay, this is the same across all the three doors. Okay, and the combined chance that the car is behind either of the other two doors is 2 by 3. Now, this is the part which you need to understand. This is door 1, this is door 2, this is door 3. The car being behind the first door or your choice is 1 by 3 as of now. And the other two doors are unknown doors. They are unknown doors. And there being a probability or there being a car behind these two doors, the probability of that is going to be 2 by 3. What is the reason? The reason is behind the second door, the chances of getting a car is 1 by 3. And behind the third door, the chances of getting a car is also 1 by 3. So this is a combined chance. I am combining the probability. The just look at it very well. This is nothing but a play of words. Okay, a play of a few sentences, and that's how the entire situation changes. The combined chance that the car is behind either of the other two doors, either, be it in this or in this. Okay, either of the two is going to be a combined probability of 1 by 3 and 1 by 3 each. When we combine them together, we get a joint probability or a combined probability of 2 by 3. This is the main equation which you had to understand. Okay, how does 2 by 3 come into play? And then the host, who knows what's behind every door, opens one of the other two doors and he always reveals a goat. Let's assume that the host opens the second door. He opens the second door and discovers a goat behind it. And you discover a goat behind it. So, what happens is when you discover a goat behind it, the probability of finding a car on the second door goes down to 0. Mark my words, I say the probability of getting a car behind door number 2 is equal to 0. Why? Because it has already been revealed that there is a goat behind door number 2. Okay? Now, this is important that his action is not random and he never opens the car door even if it is among the two you did not pick. Okay, once he opens a goat door, the second door is the goat door, you are given a choice to stick with your original pick, that is door 1, or switch to the other unopened door, which is door number 3. As I have already told you, the combined probability of 2 and 3 is 2 by 3. Now, I want all of you to open your ears and listen to me and listen to what I am trying to say. When you have two doors which were unknown, the combined probability of finding a car came out to be 2 by 3. Once one door was opened, the second door was opened, and the outcome was not favorable, and there was a goat behind it. The probability of finding a car, the probability of finding a car behind that particular door goes to 0. Okay, the probability of finding a car in door number 2 goes down to 0, but the combined probability is still 2 by 3. The combined probability is still 2 by 3 if in door number 2 the probability of finding a car is 0 and the combined probability is 2 by 3, then the probability of finding a car in door number 3 changes to 2 by 3. Okay, the combined probability remains the same, or the combined probability shifts itself to the door which is still unopened. Door number 3 now gets all the probability of getting the car, and that is equal to 2 by 3. I am only and only talking mathematically. Okay, this is not a luck game, this is a mathematics game. That is why the probability of getting a car in the first door remains to be 1 by 3, and the new probability of getting a car in the third door comes out to be 2 by 3. That is why in the first slide it says switching leads to a more probable outcome. A more probable outcome. Get it? This is how the entire situation is framed. Now, the initial 1 by 3 chance that the car was behind your original door does not change. That's when I say that the probability of 1 having a car remains 1 by 3, right? But now Monty has shown you that one of the other two doors definitely doesn't have the car. Okay, he has already shown you that one of the other two doors doesn't have a car. So all of that 2 by 3 probability that was spread across the other two doors now gets focused entirely on the one unopened door. It shifts to the third door. That means if you stick, your chances of winning stays at 1 by 3, and if you switch, your chances become 2 by 3. Therefore, switching doubles your chances of winning the car. When this says doubles your chances of winning the car, this is only and only possible in the classic 3-door problem. This is only valid for the classic 3-door problem. It is not valid for any other number of doors. Okay, it's not see this doubling is a concept, so this doubling isn't possible for any other case. I hope you've understood the entire Monty Hall problem through this situation. Now I will be taking you to one example question which is not Monty Hall, but it will give you insights into joint probability. Okay, this is also called conditional probability, but I will call it joint probability as well. Try to understand this question. There are two boxes, each containing red and green balls. Let's call this box A. Let's call this box B. The first box contains 5 red balls and 9 green balls, while the second box contains 6 red balls and 4 green balls. One of the boxes is selected at random and then a single ball is drawn from it. What is the probability that the ball drawn is green and it came from the second box? Okay. My first question to you is, what is the probability of choosing either box A or box B? What is the probability of choosing one of the two boxes? Probability is nothing but a game of favorable outcomes upon total outcomes, right? This is nothing but probability. So the favorable outcome is going to be choosing box number 2 or the second box. That means there is only one choice, which is the second box, and the total number of probabilities or the total number of boxes which are there with us are 2 boxes. So 1 by 2 is the probability of choosing the second box, right? Now, in the conditional probability that we have fulfilled the first condition, we are going to write the same output over here and use a multiplication sign to lead to the second probability that we are talking about. The second probability is that the ball drawn is green. Now we are sitting inside, right now, we are sitting inside box number 2. We are sitting inside box number 2. Now, inside this box, we are again going to apply probability. In probability, the total outcomes that we can possibly have is the 10 balls. Okay, the total instances are picking out 10 balls. Okay, and then the favorable outcomes that we are talking about is going to be the number of green balls. The number of green balls are 4. So the final answer comes out to be 1 by 2 multiplied by 2 by 10, or 1 by 2 multiplied by 4 by 10, which gives me 2 by 10. So the probability is 2 by 10, or as simple as this, that the probability is 20%. Okay, the probability is 20%. Right? Good enough. So this is how you take 2 steps in the probability. Fine. Now I'll move to the standard questions, or the questions which might be asked in the examination. See, we don't have the real questions yet. Okay, the examination center or SSC hasn't released the key yet. That is why we don't have the exact questions. But as per the pattern which is coming, as per the reviews that we are getting all over the internet, from that we have curated a few questions which have been asked. Okay, and there is a doubt problem also at the end of the presentation. Okay, at the end of the lecture. This is the first problem. Okay, this is the first problem. In the classic Monty Hall game, 3 doors, 1 car, and the host always opens a goat door. What is the probability of winning the car if you switch? Okay, I would always draw the doors with numbers. First one, second one, third one. Okay, I need to know the probability of winning the car if we switch. Let's assume the first door was your choice 1. The probability of getting a car over here is 1 by 3. Door 2 and 3 remain unopened. The joint probability of getting a car comes here as 2 by 3. This is the joint probability. The second door is open. The second door is open, and the probability of getting a car comes out to be 0 because a goat is revealed. Because a goat is revealed. So, if the goat is revealed, the probability of getting a car goes down to 0. That is why the probability of the third door having a car comes out to be 2 by 3. Why does it happen? Because in a joint probability of 2 by 3, you had door number second and you had door number third. When the second door opened, it had a goat, the probability dropped to 0. So the third door gets the entire probability of 2 by 3 of getting a car. Okay, so if I switch, then the probability of third door having a car comes out to be 2 by 3. Okay, got it? This is the standard problem. Now let me move to a little more customized questions. Now we have specially curated the long questions because there are long questions coming in the exam, so it will be better for your reading speed as well. A game show features 5 closed boxes, 1, 2, 3, 4, and 5 closed boxes. Behind one of them is a brand new car. Remaining 4 have a goat. You select one box at random. The host, who knows the contents of all the boxes, then opens 2 from the other 4 boxes, both revealing goats. Now, 2 unopened boxes remain apart from your original choice. If you decide to switch and randomly pick one of these 2 unopened boxes, what is the probability that you end up winning a car? Now, this is going to be a classic case of conditional probability as well. Listen to me very, very carefully. Okay? This is where people get tricked, and this is where all your formulas are of little use. They are definitely of use, but they are of little use now. You have chosen the first car or the first door. This is the choice 1 that you've chosen. The host opens 2. Let's assume the host has opened second and third. Both have a goat behind them. Both have a goat behind them. So, what is the probability of 4 and 5 or 4 or 5 to get a car? Okay, okay. The illustration is complete. The illustration is clear. The illustration we have over here is pretty clear. Now, I will take you to the solution directly. First of all, the choice 1 has a probability of getting a car as 1 by 5. The combined probability, the combined probability, the combined probability of getting a car in the next 4 doors is going to be 4 over 5, 1 by 5 plus 1 by 5 plus 1 by 5 plus 1 by 5. So the combined probability of there being a car is 4 by 5 in the next 4 doors. Out of these 4 doors, now you have to choose only 2 doors. And out of the 2 doors, you can only choose one of them. So, out of the 2 doors which are left unopened, and Monty has given you a choice of choosing either 4 or 5, out of these, I'll quickly change the pen because this is a different concept. Out of the, no, this is a dark color. This is good. So, out of the 2 doors which are left behind, you are supposed to choose one door. Okay, out of the 2 doors which are left behind, the probability of you getting a car is 1 by 2. So this is a conditional probability and this is a joint probability question. When I was asking you, this is a combined probability of there being 4 by 5 outcomes. Now, when I multiply 4 by 5 with 1 by 2, I am focusing down, or I am drilling down to the point where I actually get a car. Okay, when I say 4 by 5 and multiplied by 1 by 2, this becomes 2 by 5, or this simply becomes 40%. This simply becomes 40%. And this is the answer that I was looking for. Good enough? Let's move ahead. Now, as you've understood, we'll be moving just a little faster than this. You're playing a game with 5 doors. One of them has a car, 4 of them have goats. You choose one door. There are 5 doors. One, two, three, 4, and 5. We'll always assume that you use the first door. This is no bias. There is no bias in this. Okay, but just for convenience, for the sake of convenience, we choose the first door always. The host who knows opens up one of the remaining doors to reveal a goat. So this is your choice one. This is the open door which has a goat behind it. Out of the other three unopened doors, you must randomly select to choose. Okay, it says you must randomly select one to switch to. What is the probability that this switch leads to the car? So a switch has to be made. In the beginning, 1 by 5. In the beginning, 1 by 5 was the probability of choice 1. Then a goat came into the picture. What is the choice of what is the chance of choosing the next 4 doors? That is 4 over 5. The chance of choosing the next 4 doors, or the chance of there being a car in the next 4 doors, as a combined probability is 4 over total 5 doors. We'll have to multiply it now with the number of real choices we have. The number of real choices we are left with is a total number of 3 choices. And out of those 3 choices, the probability of you getting a car again, or you now getting a car, is going to be 1 by 3. So this situation comes out as 4 by 15. 4 by 15 is the probability, or 15 twos are 30. Right now I'm bringing it into the term of percentages. 15 twos are 30, 10, 15 6 are 90, and another 10, 26.66, or a 26.66 percentage, or 26.7 percentage, as simple as that. So this is my answer. Good enough. Let's move ahead. In a variation of the Monty Hall game, you are faced with 10 closed doors, behind one of which is a car and rest of them are goats. You pick one door at random. Then the host, who knows what lies behind each door, opens two of the remaining doors. Okay, there is one door here, and you get two doors opened, and dot dot dot, there are 7 more doors. Okay, the first one was choice 1. Two remaining doors have been opened, and both of them have goats in them. Okay, 7 doors are such which are a mystery. 7 doors are one which is a mystery, and you have to choose by selecting one door at random from the 7 unopened doors which you did not initially choose. What is the approximate probability that your new choice wins you the car? That means switching, the probability of switching. First of all, what is the chance of you opening these 9 doors, or there being a car in these 9 doors? The combined probability is going to be 9 over 10, that you will choose these 9 doors over the total number of 10 doors, or you will get a car in the 9 doors over all the 10 doors. So that is 9 by 10. This is a combined probability of the doors we never chose. Out of those 9 doors, 2 of them had goats. That is why I am left with 7 doors now. Out of these 7 doors, I have to choose only one, because there I will get a car. So my answer comes out to be 9 over 70. Or if you go with the chances of probability, I can say that 12 sevens are 84, right? So I am supposed to reach somewhere near 90. So 12.86 is definitely going to be my correct answer. So 12.86 percentage is the correct answer. Look how beautifully smooth this question has become for you. So we are now solving the next question. Here it says that here it says that there are 7 closed doors where you would get just a second, 7 closed doors, and one has the car and everything. Fully aware, he opens 2 others doors. So let me first choose one. He has opened 2 doors. Both of them have goats. There are how many? These are 3. There are 4 more doors which are unopened, and the first one was your choice number 1. Now, what you have to check is, what is the closest estimate of your chances of winning the car when you decide to switch. See, it says here, if you decide to switch. Now, firstly, what is the chance of you? What is the chance? What is the chance of you picking 6 of these doors out of the 7? That is 6 upon 7. Or what is the chance of there being a car behind 6 of these 7 doors? That is 6 upon 7. This is nothing but a combined probability of these 6 doors, 6 over 7. Now, using conditional probability, there is a second level of choice which you need to check. What does the second level of choice say? You have 4 doors which are unopened, and you will get a car in one of them. You'll get a car in one of them. So 6 by 7 into 1 by 4, and this would give me a probability of 3 by 14. Or when I multiply it by 100 and give the answer in percentages, 14 2s are 28, another 2, 14 1s are 14, another 6, 14 4s are 56. So somewhere around 21.4% is my answer. All right, I hope you've understood this. Moving forward, just 2 more problems to go, and then you will be free of this tension in your brain. Now, this is not a difficult question, but the wordings are such that you might feel this is difficult. You're on a futuristic space mission, and the ship's AI, artificial intelligence, represents you with 100 identical looking energy capsules. Okay, there are 100 of them. Only one of which contains the rare quantum core needed to power your return home. You select capsule number 7. Okay, you select capsule number 7. There are a few capsules here, there are a few capsules there. You choose capsule number 7. Let's say that there are, if you leave behind all the other capsules, there is the 7th capsule, and you have 99 more capsules. Okay, this is your first choice. You select capsule number 7. Moments later, the AI scans the remaining capsules and deactivates 97 of them. 97 of them are gone. That means they are useless, confirming that they were empty. You are now only left with how many more capsules? Just 2 more capsules. Only capsule number 7, your original choice, and capsule number 88. Capsule number 88. Just a second. Is there something that I'm missing? Let me read it once more. Only one of which contains the rare quantum core needed to power your return. You select capsule number 7. Moments later, the AI scans the remaining capsules and deactivates 97 of them, confirming they were empty. Only capsule number 7 and your original choice and 88 remain active. The AI then tells you that the quantum core is hidden in one of the 2 remaining capsules. Yeah, one of the 2 remaining capsules is hidden in one of the 2 remaining capsules. What is the most reasonable estimate of the probability that capsule 88 contains the quantum core? Okay, out of this 97 are gone. 97 are gone. Just like so many examinations have a few errors in them, and this could have definitely been a speed breaker for your exam. I have found out a very very small and minute error which is actually demolishing the entire problem. The total number of capsules which were deactivated, AI scans the remaining capsules and deactivates 97 of them. It cannot deactivate 97 of them, it has to deactivate 98 of them for the question to go on. Okay, instead of deactivating 97, it has deactivated 98, and there is only one choice left. There is only one choice left, right? So there is only one choice left, and this one choice that is left is the 88th capsule. So what is the probability of you switching to the 88th capsule, and it also has the quantum core? This is the question. So the 7th is the first choice and the 88th is your second choice. 88th is your second choice. So what is the probability of you choosing the remaining 99 capsules over your first choice, which was the 7th capsule, out of the 100 choices? So there being the quantum core in the 99 or in the rest of the capsules is 99 over 100. Now against that 99 over 100, you're only left behind with the 88th capsule. You're only left behind with the 88th capsule. So what is your chance? What are your chances of choosing the 88th capsule among the total 88 capsules? That means you only have one choice of choosing the 88th capsule. There is no internal probability that we have to select from. That is why I'm writing 1 over 1 over here. So 99% is my final answer. Okay, 99% is my final answer. Got it? Moving forward, now this is a doubt problem which has come to me, and I believe somebody else must have taught it too. So I'll be quickly figuring it out. There are four doors. There's one, and there are two, three, and four. There are four doors. Behind the three doors, assortment of gummy bears, and the remaining door has pure gold car behind it. You pick a door, then the host reveals a door which he knows is only with a couple of red gummy bears. Then you're given the choice to stick with your first choice or switch to the other two unopened doors. Okay, this had a gummy bear in it, and this one had, this was your first choice. This is your first choice. Now there are two doors which are left unopened. Out of these three doors, out of these three doors, what is your chance of getting the gold car? That is 3 over 4. Out of three doors, the combined probability of you getting a car is 3 over 4. Now, out of the two doors which were left behind, you have the chance of getting a car in only one door. So 3 by 8 is your answer, which is also, 3 by 8 is your answer. Now, here comes the difficult part. If the probability that you will win the car, if you switch, is A over B, where A and B are co-prime positive integers, what is A plus B? I have gotten the value of A over B as 3 by 8. Okay, this is nothing but A over B. When we say that A and B are co-prime, that means both of them have been cancelled out to the least possible number. Like 3 ones are 3 and 8 ones are 8. There is nothing more common in between them. So both of them are positive. What is A plus B? The value of A is 3, the value of B is 8. So A plus B is nothing but 3 plus 8, which is equal to 11. And this was a doubt problem which was sent to us in the group. So that is why we are solving it here. Got it? So I think we've covered the entire thing. And now nobody would have even the slightest problem in solving questions from the Monty Hall problem. Right? Thank you.